a mysterious phenomenon occurred at the end of the Paleozoic era. The global ocean level dropped sharply, exposing vast continental shelf areas. This event, known as marine regression, took place around 250 million years ago, at the end of the Permian period. As a result of the sudden drop in sea level, many marine ecosystems were threatened. For example, coral reefs that had thrived in tropical waters began to suffer from water shortages, and organisms dependent on their existence faced extinction. Sea urchins and mollusks that inhabited these regions were unable to adapt to the changing conditions and massively died out. Exposed coastal zones turned into lifeless plains where life had once flourished. On land, the same thing happened. Ecosystems on the verge of the sea lost their familiar habitats. Marine flora, such as algae and phytocoenoses, also suffered. Their diversity sharply decreased, leading to a reduction in food sources for many species. Research shows that many marine organisms could not survive without the usual saltiness and water pressure. As a result, ecosystems dependent on stable sea levels began to transform. Marine creatures were replaced by terrestrial organisms, but these were not the ecosystems that had existed before. These changes affected not only the animal and plant worlds, but also geological processes. Exposed marine deposits, which had been part of the seafloor, began to erode under the influence of wind and rain. This led to the formation of new landscapes that became the basis for future ecosystems. The established ecosystems eventually adapted to the new conditions, but the process of restoration took millions of years. By the time the sea level began to recover, many species had already disappeared forever, and new ones took their place. This period laid the foundation for further evolution of life on Earth, where adaptation to changing conditions became a key factor for survival. According to paleontologists at this time, a significant number of species went extinct, which later led to the Permian Triassic mass extinction. One of the most massive in the history of our planet, when up to 95% of all marine species perished. Scientific research shows that this marine regression played a decisive role in changing the biosphere, leading to large-scale evolutionary changes and the appearance of new species adapted to the new conditions. Gradually, after the end of the Permian period, life on the planet began to recover, but with each new stage of evolution, it left behind those who could not adapt to the harsh conditions. The marine regression at the end of the Permian period became not just a natural phenomenon, but a catalyst for changes that defined the appearance of life on Earth in the future. Transport yourself back to the time when Earth's atmosphere was first filled with oxygen, creating conditions for the development of complex life. This occurred approximately 2.5 billion years ago during the Great Oxygenation event, when photosynthetic organisms such as cyanobacteria began actively producing oxygen as a byproduct of photosynthesis. These microorganisms used sunlight to convert carbon dioxide and water into organic compounds, releasing oxygen in the process. Evidence of this process has been found in ancient shales, such as stromatolites, which formed as a result of cyanobacterial activity and are preserved in geological layers. As oxygen accumulated in the atmosphere, there was a gradual transition from anaerobic to aerobic conditions, leading to a true revolution in Earth's ecosystems. Around 2 billion years ago, the oxygen level in the atmosphere reached approximately 1%, but this level continued to rise, and by the beginning of the Paleozoic era, oxygen became the primary component of the atmosphere. This change allowed organisms that used oxygen for respiration to evolve, opening up new metabolic pathways, including cellular respiration, which significantly increased energy efficiency. The appearance of aerobic metabolism allowed organisms to obtain several times more energy than with anaerobic processes, opening up new horizons for complex life. As a result, at the beginning of the Paleozoic, multicellular organisms such as trilobites, mollusks, and the first fish began to appear on Earth. These animals had more complex anatomy and physiology, allowing them to occupy diverse ecological niches. Oxygen also facilitated the appearance of the first multicellular algae, which became the primary producers in marine ecosystems. During this time, there was a sharp increase in the diversity of life forms known as the Cambrian explosion, which began around 540 million years ago. During this period, the main groups of organisms, such as echinoderms, mollusks, and the first ancestors of vertebrates, emerged. The oxygenation event changed the chemistry of Earth forever, creating conditions for complex ecosystems and biomes that we see today. Scientific research shows that the oxygen level in the atmosphere fluctuated over millions of years, but it was during this period that it reached a critical threshold, playing a key role in the evolution of life. Allow yourself to immerse in a world where life's music first resonated, the buzzing of insects and the song of the first terrestrial vertebrates. In the Paleozoic era, around 300 million years ago, nature underwent revolutionary changes, and it was during this time that the first sounds made by land animals began to emerge. Buzzing insects like fossilized grasshoppers started their history in the Devonian period when they adapted to life on land. These creatures used sound communication to attract mates and protect themselves from predators. For example, Archaeopteryx, one of the earliest known representatives of the class of birds, could produce sounds that aided it in hunting and communicating with its kin. The appearance of vocal signals in amphibians like early frogs was a significant step in the evolution of terrestrial animals. These amphibians, living both in water and on land, used various sounds to attract females and mark their territory. Research by paleontologists shows that some species could produce sounds reminiscent of modern frog calls, reaching frequencies up to 2000 Hz. Sound communication provided evolutionary advantages, allowing animals to better navigate space, find mates for reproduction, and avoid predators. This led to the formation of complex social structures and interactions within ecosystems. Animals capable of sound communication had a better chance of survival and reproduction. As a result, each new evolutionary form of life, whether it was a dragonfly with its loud wing rustle or an early amphibian ancestor with its simple yet effective sound signals, contributed its unique part to the overall symphony of life. This process became the foundation for the further development not only of terrestrial vertebrates, but also of ecosystems as a whole, where sounds became an integral part of the interaction between species. Ultimately, it was during this period that sounds of life began to fill the continents, transforming quiet landscapes into dynamic musical scenes where every insect and every animal was part of a vast symphony of nature. Scientific research conducted in the 20th century showed that sounds can influence the behavior of both predators and prey, confirming the importance of sound communication in evolution. The buzzing of insects filling the air became not just background noise, but a fundamental element of biosynthesis, shaping not only ecological, but also social relationships between organisms. In ancient times, there existed forests unlike any modern ones, without a single flower or tree as we understand them today. These coal forests, which thrived more than 300 million years ago, formed an ecosystem dominated by giant ferns, horsetails, and horsetails. The height of these ancient plants reached 30 meters, creating a dense and humid atmosphere filled with the scent of decaying vegetation. Imagine walking through this prehistoric forest. Underfoot, mossy carpets of fallen leaves crunch, and the air is saturated with moisture, as if in the tropics. The sounds of ancient insects, such as giant dragonflies, fill the space, with their wingspans sometimes exceeding 20 centimeters. On the trunks of giant ferns, you can see the traces of long-extinct animals that left their imprints in the soft soil. These forests did not know flowering plants, which only appeared much later, during the Mesozoic era. Each plant in this forest played its role in the complex food chain. Spiders and mollusks were the primary herbivores, feeding on the leaves of ferns and horsetails, while large predators like meganeuras and other ancient insects hunted them. The complex root systems of ferns helped retain moisture in the soil, creating ideal conditions for growth. These forests laid the foundation for the formation of coal, which we use today, millions of years later, when the pressure and heat caused the plant remains to harden into black coal seams. Looking at these forests, it is hard not to be amazed at how life on Earth changed in response to the climate conditions that prevailed then. The coal era serves as an important reminder of how the diversity of life and ecosystems can change depending on factors such as climate and geology. The ancient forests of the Carboniferous period witnessed the evolution of life, preparing the ground for the appearance of the first terrestrial animals that would soon inhabit this planet. Their existence proved that life always finds a way to adapt and evolve, even in the harshest conditions. The puzzle lies in the fact that scientists still debate why certain groups of animals survived catastrophic mass extinctions, while others disappeared forever. An example of life finding its way is the Permian extinction, which occurred around 250 million years ago, when over 90% of all marine species and around 75% of terrestrial animals went extinct. However, some groups managed to adapt and survive in these extreme conditions. For instance, the ancestors of modern amphibians, such as Eriops, had the ability to hibernate, which allowed them to endure unfavorable conditions like rapid temperature drops and food shortages. These organisms could enter a state similar to hibernation, slowing down their metabolism and oxygen consumption, thus enabling them to survive until more favorable times. Omnivory also played a crucial role in survival. For example, the ancestors of crocodiles could consume both plant and animal matter, giving them an advantage in conditions where traditional food sources became unavailable. Research conducted in the 20th century shows that tolerance to low oxygen levels was a key factor. For instance, some ancient fish developed special hemoglobin that allowed them to efficiently use oxygen even in conditions of its scarcity. Fossils indicate that the surviving organisms had a broader range of shapes and sizes, which helped them adapt to new conditions. The world after the apocalypse looked like a desolate space where only a few surviving organisms began to repopulate the planet. Open spaces once teeming with life were now covered in dust and debris, while small groups of amphibians and reptiles slowly colonized new ecosystems that were forming in place of the destroyed ones. Meanwhile, in the water bodies, fish began to re-emerge, as evidenced by the remains, adapting to new conditions and developing more efficient breathing methods. The ability to hibernate, omnivory, and tolerance to low oxygen levels became the main characteristics that helped the surviving groups recover in this new, hostile world. Scientists suggest that such adaptations ensured survival over millions of years when life on the planet was on the brink of extinction. These traits allowed the survivors not only to endure, but also to restart the process of evolution in conditions that once seemed insurmountable. Over millions of years, the surviving organisms continued to evolve, creating new species and adapting to changing environmental conditions. There were also other groups that managed to survive through reproductive strategies. For example, some insect species began to produce a large number of offspring, increasing their chances of survival in conditions of high mortality. This strategy allowed them to quickly colonize new territories and occupy niches left vacant by the disappearance of other species. Do you know that life on Earth has experienced several global apocalypses? The Paleozoic era, spanning from 600 million to 250 million years ago, is one of the most dramatic and remarkable periods in the history of our planet. This time witnessed not only the rapid development of life but also several major mass extinctions, with the Permian extinction being the most significant, occurring around 250 million years ago. This event wiped out 95% of all marine species and more than 70% of terrestrial species, effectively erasing entire ecosystems from the face of the Earth. The Paleozoic era is divided into 6 periods: Cambrian, Ordovician-Silurian, Devonian, Carboniferous, and Permian, each characterized by unique forms of life and geological changes. For example, the Cambrian period, which began around 530 million years ago, is marked by a burst of biodiversity known as the Cambrian explosion, when nearly all major animal groups that exist today appeared. At this time, the first invertebrates and the ancestors of vertebrates, such as primitive fish, emerged. The Ordovician period, which followed, is known for its diverse marine organisms, including trilobites and corals. However, around 444 million years ago, the first mass extinction occurred, when about 18% of all taxa disappeared due to rapid climate changes and a drop in sea level. The Silurian and Devonian periods brought further development of life on land. The first land plants and insects appeared. Around 360 million years ago, during the Devonian period, the first amphibians emerged on Earth, marking a significant step in the evolution of vertebrates. However, this period was also marked by the second mass extinction, when about 75% of all species, including many fish and marine invertebrates, disappeared. The Carboniferous period is known for its vast forests and biodiversity, but it too was not spared from catastrophes. The third mass extinction occurred at the end of the Permian period, when volcanic activity and climate changes led to catastrophic consequences for ecosystems. Throughout the Paleozoic era, life on Earth faced numerous challenges and changes, and each of these catastrophes left its mark on the evolution of species. The scale of time in hundreds of millions of years allows us to imagine how life developed in conditions of constant change, from small marine organisms to giant trees and the first vertebrates. This era was not only a time of ascent, but also of decline, when nature, like an artist, recreated its masterpieces after each catastrophe. The Paleozoic era lasted around 300 million years, and during this time, significant changes occurred, making evolution seem to go in circles, but each new cycle brought new forms of life. By the end of the Paleozoic era, during the Permian period, Earth already looked different. By this time, supercontinents such as Pangaea had formed, which also had a significant impact on climate and biological diversity. The Paleozoic era laid the foundation for the further development of life on the planet, and its legacy continues to influence our understanding of evolution. An important fact is that the Paleozoic era was the first stage where life on land acquired stable forms such as forests and land animals, opening the way to the future diversity that we observe today. It will be interesting to learn that the first animals to conquer the land were not vertebrates, but arthropods the size of a coin. During the Silurian period, around 400 million years ago, the shores of ancient oceans began to see the first terrestrial forms of life. Notable representatives of this time were ancient millipedes and crustaceans, which adapted to life on land through numerous evolutionary changes. Their bodies were covered in a hard, chitinous shell that protected them from dehydration and allowed them to survive in these new conditions. These animals developed waterproof coverings, which was a crucial factor in their adaptation to the terrestrial environment. They also acquired tracheae, a specialized respiratory system that allowed them to breathe air, which was necessary for survival away from water. The sizes of these first terrestrial inhabitants varied from a few millimeters to several centimeters, and their appearance resembled modern insects with long legs and a segmented body. Their diet consisted mainly of decaying plant material. They played a key role in ecosystems by breaking down organic matter and contributing to the formation of soil. In the Devonian period, around 360 million years ago, these creatures continued to evolve, and larger forms such as ancient scorpions and spiders began to occupy new niches in the ecosystem. These creatures inhabited the coastal zone where water and land met, creating a unique environment for the first steps on land. The moist sand and mud beneath their legs, the gentle sea breeze, and the sun's rays created conditions in which life could develop and thrive. These pioneers, pushing through vegetation, became the foundation for future ecosystems, which ultimately led to the appearance of more complex forms of life. Right in this environment where the sea meets the land, the history of terrestrial life began, and these arthropods became the first architects of a new ecosystem. The first terrestrial arthropods, such as Silurian eurypterids, reached lengths of up to 1 meter and used their predatory abilities to hunt small marine creatures, which also contributed to their survival. These events laid the foundation for the formation of the biosphere, in which life began to actively develop on land, creating conditions for the appearance of more complex organisms. Amazingly, the coal that warms our homes is the remains of ancient forests that are over 300 million years old. During the Carboniferous period, which lasted approximately from 360 to 290 million years ago, Earth was dominated by tropical conditions where vast swampy areas were covered with dense forests. These forests, primarily composed of conifers and ferns, created thick layers of vegetation that were eventually submerged. The waterlogged environments filled with water did not allow decomposing organisms, such as bacteria and fungi, to effectively break down the plant remains. This led to the accumulation of enormous masses of organic material, which gradually sank under layers of mud and sand. The process, spanning millions of years, was slow but majestic. Under the pressure of subsequent layers of sediment, temperature and pressure gradually increased, transforming the cellulose of the vegetation into coal. Initially, peat formed, which over time, under the influence of pressure and temperature, transformed into lignite, then into bituminous coal, and finally into anthracite, the highest quality coal. Research shows that in some regions, such as the Appalachians in the USA, coal seams can reach a thickness of up to 100 meters, indicating how abundant these ancient forests were. Coal formed under conditions where the level of oxygen in the atmosphere was significantly lower than today's, which helped preserve the organic material. These coal seams are now the primary source of energy for millions of people around the world, despite their formation taking millions of years. Scientific research shows that coal extracted from these seams retains information about the climate and ecosystems of that time, making it not only a source of energy, but also an important object for studying the ancient conditions of life on our planet. Strangely, the first creatures to emerge onto land were neither plants nor animals in the way we understand them today. They were fungi, lichens, and microorganisms that began to slowly but surely colonize lifeless patches of land. Around 400 million years ago, during the Devonian period, the first fungi, such as those of the Myxomycetes genus, appeared on land. These organisms played a crucial role in weathering rocks, breaking down minerals, and releasing nutrients essential for soil formation. Studies show that fungi can decompose complex organic compounds, significantly accelerating the process of soil formation. Lichens, which consist of symbiotic relationships between fungi and algae, also contributed to this process. They formed thin films on rocks, allowing them to capture moisture and atmospheric gases, creating conditions for further rock decomposition and the formation of primary soils. For example, lichens of the Cladonia genus can survive in the most inhospitable conditions, including Arctic regions, demonstrating their remarkable resilience and adaptability. Microorganisms, such as cyanobacteria, also played a significant role by fixing atmospheric nitrogen and enriching the soil with necessary elements. These small but powerful organisms created the initial conditions for life, forming an ecosystem in which more complex organisms could later appear. As these microorganisms, fungi and lichens slowly colonized the land, they gradually transformed lifeless rocks into fertile soils. As a result of this process, by the end of the Devonian period, the first land plants appeared, marking an important stage in the evolution of life on Earth. These primitive organisms, by forming symbiotic relationships, not only improved conditions for their own survival, but also prepared the soil for future forests, which in turn became homes for diverse fauna. Ultimately, these small organisms became the foundation for the formation of complex ecosystems that we know today. Scientists have calculated that it can take up to 1,000 years for soil to form, during which microorganisms slowly but surely process and transform rocks into fertile layers. This creates a unique cycle in which life supports life, starting with the most inconspicuous forms. Amazingly, before the arrival of sharks, armored fish resembling underwater tanks dominated the seas. These ancient creatures, known as placoderms, thrived during the Devonian period, which lasted approximately from 411 to 360 million years ago. Placoderms had a unique appearance. Their front part of the body was covered with a massive bony armor, giving them a fearsome appearance and making them virtually invulnerable to many marine predators of the time. The armor was not just a protective shell, but a complex structure consisting of numerous bony plates that effectively protected the soft tissues from attacks. These fish had primitive jaws with sharp teeth, allowing them to hunt other marine creatures, such as invertebrates and small fish. Examples of such placoderms, like the lake dinosaur Dunkleosteus, which could reach lengths of up to 8 meters, demonstrate how formidable these predators were. Their powerful jaws could easily tear apart the shells of their prey, making them some of the most dangerous creatures of their time. In the Devonian seas, teeming with diverse life forms, placoderms held a significant place in the food chain, acting as the main predators. These fish were not only strong but also incredibly adaptable. For instance, their ability to move quickly allowed them to hunt smaller and faster creatures, while their hard armor protected them from competitors. At this time, the marine ecosystem was incredibly diverse, and placoderms, with their fearsome appearance and predatory lifestyle, became a symbol of strength and survival in the face of fierce competition. These marine tanks not only survived in harsh conditions, but also significantly influenced the evolution of fish in general. Scientific research shows that placoderms were the predecessors of modern fish, underscoring their importance in the evolutionary chain. Their existence sparked the development of new species, ultimately leading to the emergence of sharks, which became the dominant group of marine predators. The remarkable ability of placoderms to adapt to changing environmental conditions allowed them to survive for millions of years until they began to disappear at the end of the Devonian period. At this time, their place was taken by more modern fish, which developed and changed, but it was the placoderms who laid the foundation for the further evolution of marine predators. Today, scientists find fossil remains of placoderms that help us better understand their way of life and the ecological niche they occupied in ancient seas. For example, finds in the United States and Europe show that these fish were widespread over large territories and could adapt to various conditions. At first glance, it may seem that evolution is a gradual, smooth process, but the Paleozoic era demonstrates the opposite. Over this period, which spanned from 630 million to 250 million years ago, life on Earth experienced long epochs of stability interrupted by sudden bursts of speciation and mass extinctions. For example, at the end of the Ordovician period, around 440 million years ago, one of the largest mass extinctions in history occurred, with approximately 85% of all marine species disappearing. This event was likely caused by a sudden cooling of the climate and changes in sea level. Such events created conditions for the emergence of new ecological niches, which were quickly filled by new species once the conditions stabilized. In the Devonian period, which began around 400 million years ago, there was a so-called fish explosion, when the first true fish and the ancestors of all terrestrial vertebrates appeared. This period was also marked by significant changes in plate tectonics, which contributed to the formation of new continents and changes in ocean currents. Asteroid impacts at the end of the Permian period, around 240 million years ago, were a catastrophic turning point that led to the extinction of more than 95% of all species on Earth, paving the way for the rise of dinosaurs in the Mesozoic era. These sudden changes in the environment, caused by both internal planetary processes and extraterrestrial factors, created conditions for evolutionary leaps. The Paleozoic era is not just a collection of data on extinctions and speciation, but a true arena where life was constantly forced to adapt to changing conditions. For instance, during the Carboniferous period, which began around 360 million years ago, tropical forests became the basis for the emergence of the first amphibians. This happened because terrestrial life began to colonize new ecosystems where plants and animals interacted in a complex food chain. Each of these events, whether climate changes or tectonic movements, underscores that evolution is not a linear process, but a chaotic and unpredictable path filled with unexpected turns and opportunities. Ultimately, the Paleozoic era was a period where each change in the ecosystem could lead to a new evolutionary leap, encompassing all levels of life on the planet. In this context, the period from the Triassic to the Jurassic, around 200 million years ago, demonstrated how life on Earth, on the brink of extinction, could quickly adapt and expand as soon as conditions became more favorable. Imagine a sea teeming with creatures resembling giant scorpions the size of humans. These formidable arthropods, known as eurypterids, inhabited the waters of the Silurian period. Approximately 400 million years ago, they could reach lengths of up to 2.5 meters, making them some of the largest marine predators of their time. Eurypterids possessed massive claws which they used not only for hunting, but also for defense. Their powerful mandibles could tear apart prey, as evidenced by fossilized remains showing bite marks on the shells of other marine creatures. These predatory beings were not confined to the water. They could venture onto land, giving them an advantage in the struggle for survival. Scientific research conducted in the 1990s by paleontologist Dr. Eric Lawrence revealed that eurypterids could spend time in shallow waters, where they searched for food and shelter from predators. The coastal waters of the Silurian period were teeming with life and diversity, with eurypterids occupying the top of the food chain. These creatures could hunt smaller marine invertebrates and even other eurypterids. Their presence in the ecosystem indicates complex interactions between species and the crucial role of predators in maintaining balance in the marine environment. Studies suggest that eurypterids may have been the predecessors of later predators like sharks and marine reptiles. Their fossils have been found in places such as Scotland and North America, where geological layers testify to the rich marine life. Preserved specimens show that eurypterids had a hard exoskeleton that protected them from predators and allowed them to survive in various conditions. Looking at these ancient creatures, one can see how evolution shaped marine ecosystems, creating conditions for further development of life on Earth. Eurypterids, with their unique characteristics and adaptations, were not just predators but true monsters of their time, leaving an indelible mark on history. Their disappearance at the end of the Silurian period was a significant milestone in the evolution of marine ecosystems. The existence of these creatures and their adaptation to their environment highlight the complexity and diversity of life on our planet. Their size and behavior inspired numerous myths and legends, and they have become a subject of study for paleontologists interested in the origin and development of predatory organisms in marine ecosystems. Have you ever wondered what the first reptiles on Earth looked like? In the Permian period, which lasted from 30 to 12 million years ago, the first representatives of a group that we now know as reptiles appeared. One of the earliest known members of this group was Gilo, a small creature that reached only 30 centimeters in length. Gilo had characteristic scaly skin, which allowed it to adapt to dry environments and protect itself from water loss. These reptiles began to lay amniotic eggs, a unique evolutionary innovation that allowed them to reproduce away from water bodies. This was a breakthrough because previous types, such as amphibians, depended on water for reproduction, which limited their ability to colonize new territories. Amniotic eggs had a hard shell that protected the embryo from external influences and allowed it to develop in various environments. Thanks to this, reptiles were able to occupy ecological niches on land, opening new horizons for their further evolution. Unlike amphibians, which needed water for reproduction, reptiles became less dependent on aquatic environments, which facilitated their spread across the planet. These small but effective creatures became the foundation for future reptiles, including dinosaurs, which later dominated the world. Among other early reptile species, we can mention diapsids, which appeared later and quickly adapted to various climatic conditions. Their bodies were also covered in scales, allowing them to survive in hot and dry conditions. These anatomical and reproductive strategy changes were key in the process of colonizing new ecosystems as reptiles began to migrate to land and settle in new habitats. Reptiles not only took over places previously accessible only to amphibians, but also began to develop adaptations such as thermoregulation, which allowed them to effectively use solar energy. Over time, these evolutionary changes enabled reptiles to dominate ecosystems, forming various food chains and interactions, ultimately altering the appearance of Earth's life. The ability of their reproduction in terrestrial conditions made reptiles one of the most successful vertebrates on the planet. As a result, reptiles like Gilo and their descendants became the main inhabitants of land, conquering new ecological niches and influencing the evolution of other species. Imagine a world where there are no trees, no blades of grass, and the land is a lifeless desert. This was the Cambrian period, which began around 540 million years ago and marked the first epoch of the Paleozoic era. At that time, continents were barren rocks devoid of vegetation, barely rising above the ocean's surfaces. While the land was silent, the seas below were teeming with life, and it was here that the evolution of complex organisms began. One of the most notable events of this period was the so-called Cambrian explosion, during which a multitude of new animal species appeared over a relatively short period of about 10 million years. These creatures, such as trilobites, the ancestors of modern crabs, and the precursors of chordates, filled the ocean waters, creating ecosystems that were vastly different from anything that had existed before. Paleontologists like David Rosen and his colleagues note that this period was a true laboratory for nature's experiments, as natural selection led to the emergence of complex forms of life. The Cambrian period was also characterized by the formation of the first hard exoskeletons, which provided protection and allowed organisms to survive in competitive environments. These exoskeletons, composed of calcite, have helped preserve the fossils we find today. It is important to note that the oceans during this period were very warm, which facilitated the active metabolism of organisms. For example, water temperatures could reach 30 degrees Celsius, creating ideal conditions for life. Microscopic organisms such as radiolaria and diatoms filled the oceans, forming the basis for future ecosystems. At this time, the first multicellular organisms also began to develop, marking a significant step in evolution. Continents, mostly located in the southern hemisphere, moved and changed shape, influencing climate and sea levels. Ocean currents, in turn, facilitated the exchange of genetic material between different groups of organisms, increasing the diversity of species. It is worth noting that the first organisms with eyes appeared during the Cambrian period, which can be seen as a step towards the development of more complex forms of life. These eyes, although simple, allowed creatures to better navigate their environment and avoid predators. During this period, significant changes occurred in the biosphere, laying the foundation for further development of life on Earth. The Cambrian period lasted for about 80 million years and served as the basis for subsequent evolutionary changes that led to the appearance of many species known to us today. In those times when the land was almost lifeless, the first pioneer plants began their cautious conquest of the New World. During the Silurian period, which lasted from 445 to 420 million years ago, the first land plants, such as mosses and algae, began to appear, colonizing shallow waters and moist places. These plants did not have roots as we are accustomed to seeing, and their structure was primitive. They relied on absorbing water and nutrients directly through the surface of their cells, making them dependent on the constant moisture of their surroundings. The height of these early plants rarely exceeded a few centimeters, and they formed low green islands of life among bare rocks and exposed lands that were still unfamiliar with the diversity of ecosystems. With the transition to the early Devonian period, which began approximately 420 million years ago, these plants began to diversify. For example, researchers found fossilized remains of ancient seed plants, such as Cooksonia, which were among the first land plants to possess stems and spores, but still lacked true roots or leaves. These plants did not exceed a height of 30 centimeters and typically grew near bodies of water, where the moisture in the air facilitated their survival. Their structure could be compared to modern mosses, but Cooksonia had a more complex structure, indicating the early stages of the evolution of land flora. In this silent world where life was just beginning to awaken, the green islands gradually filled the gaps between the rocks, creating the first green vegetation on the planet. These plants became the foundation for the further development of more complex ecosystems, and their existence opened new horizons for other forms of life. As the plants evolved, they began to alter their surroundings, creating conditions that favored the appearance of new species. By introducing oxygen into the atmosphere and retaining moisture in the soil, they prepared the ground for larger and more complex forms of life, such as ancient forests, which would develop in future geological epochs. Thus, in the harsh climate and limited diversity, the first plants began to form an ecosystem in which life could exist and develop. Scientists have discovered that it was during this period, the Devonian period, that there was a true boom in the evolution of land plants, leading to the formation of the first forests, consisting of tree ferns and horsetails. It is important to note that these pioneers became the basis for the further evolution of the plant world, which continued for millions of years. Contrary to popular belief, the first forests on Earth had nothing in common with modern ones and more resembled alien landscapes. These forests emerged during the Devonian period, approximately 360 million years ago, and were primarily composed of Archaeopteris, unique plants that were the first woody forms of life on land. Archaeopteris reached heights of up to 30 meters, but their appearance was extremely unusual. Instead of the familiar leaves, they had only simple, spiral green structures resembling pine needles. This created the impression that the forest was a strange, primitive realm where everything was not as in our familiar world. The wide and branched trunks of these trees resembled the trunks of giant mushrooms, and their bark was covered with protrusions and rough textures, giving them a look that could have adorned any science fiction novel. Archaeopteris not only changed the appearance of the planet, but also created the first shade which allowed other forms of life on land to develop. Each new forest mass became a kind of experimental platform for evolution. In such forests where semi-darkness reigned due to the high trunks, conditions were formed for the appearance of the first terrestrial animals. These conditions favored the development of new ecosystems where the symbiosis between plants and animals was just beginning to manifest. Since Archaeopteryx did not have true leaves, their photosynthetic capabilities were limited, which meant they could only survive in certain conditions. This created a unique dynamics in the forest, where each plant, each creature played its role in the complex chain of life. In such forests, loose soils rich in organic matter from the decaying remains of these ancient plants formed, which in turn attracted the first terrestrial invertebrates, such as insects. These insects may have been the first pollinators, contributing to the diversity of plant life. The primitive forests of the Devonian period were not only the habitat of Archaeopteryx, but also a laboratory for evolution, where conditions were created for the appearance of more complex forms of life. Although these forests were not like modern ones, they played a key role in shaping the ecosystems we know today. Archaeopteryx, as the predecessors of true trees, became an important stage in the history of our planet, leaving traces that we can study today. Their structure and growth characteristics became the basis for the further evolution of woody plants, and it was they who prepared the ground for the appearance of more complex forest ecosystems that arose in subsequent geological epochs. Try to imagine a world where birds do not sing in the sky, grasshoppers do not chirp in the grass, and bees do not buzz in the air. This was the early Paleozoic period, approximately from 500 to 400 million years ago, when life on land was just beginning to awaken, but the acoustic landscape remained eerily silent. Continents at that time were covered with scattered ecosystems, and the sounds familiar to us today were absolute fantasy. No sound disturbed the silence except for the rustling of wind, which carried away dust and sand, and the soft hum of water in rivers that flowed slowly over rocky shores. At this time, only the simplest organisms, such as algae and bacteria, could exist on the surface of the earth, creating inconspicuous greenery that could not produce any sound. This was a world where even the simplest forms of life remained underwater, as there were no vertebrates on land that could disturb the silence. Silence enveloped the expanses, and it was like an alien landscape where there was no sound, no movement, only emptiness and silence. The water in the rivers sparkled in the sun, but did not stir the leaves, as trees had not yet taken their places in the ecosystem. Along the coast of the sea, there were no sounds of waves crashing against the rocks, nor cries of seabirds, as they had not yet appeared in this world. This period of silence lasted until the revolution in the biosphere, when the first terrestrial animals began to emerge onto land, such as fungi, mosses, and later, more complex organisms. Without them, continents remained dead, and only over time did ecosystems begin to form that could fill this world with the sounds of life. Around 400 million years ago, when the first vertebrates, such as the ancestors of fish, appeared on Earth, the world began to change. These creatures who first left the ocean began to create acoustic landscapes that we know today. At first, they behaved cautiously, as if afraid to disturb the silence, but gradually, with the development of evolution, they began to fill the space with sounds. At this moment, acoustic signals began to emerge, which became the basis for complex ecosystems, where life was bustling and every corner was filled with the sounds of its inhabitants. In a mysterious manner, approximately 440 million years ago, more than 85% of all marine species disappeared, and scientists still debate the causes of this catastrophic event, known as the Ordovician-Silurian extinction. This was the first of 5 mass extinctions in Earth's history, occurring in 2 phases, the first around 440 million years ago, and the second approximately 430 million years ago. The scale of this event was enormous. Groups of organisms such as trilobites, brachiopods, and many types of corals and mollusks vanished. For instance, trilobites, which were among the most diverse and widespread marine creatures of the time, experienced a significant reduction in species, which affected the entire ecosystem. It is likely that the primary factors leading to such a massive extinction were rapid climate changes and fluctuations in sea level. Glaciation, which began at the end of the Ordovician period, could have caused significant cooling, leading to changes in ocean salinity and worsening conditions for many marine organisms. Studies show that sea levels dropped sharply, which also contributed to the destruction of familiar ecosystems such as shallow reefs and coastal zones, where many species found shelter and food. Additionally, during this time, tectonic processes were occurring, altering the configuration of continents and oceans, which could have influenced the migration and interaction of species. These events constituted a kind of catastrophe that altered the course of evolution, providing opportunities for the emergence of new groups of organisms, such as ancient fish and the first land plants, which began to fill the vacant niches. As a result of this extinction, which is considered one of the most significant in Earth's history, there were profound changes in marine ecosystems, and new species adapted to the changed conditions. The Ordovician-Silurian extinction was a pivotal moment in evolution, demonstrating how rapidly and drastically life on Earth can change. Scientists continue to study samples found in places like Canada and Sweden, where well-preserved fossil remains of organisms from that time are abundant, allowing for a deeper understanding of how this mass extinction unfolded and which species were most vulnerable. Incredibly but true, long before dinosaurs existed, there were reptiles that were almost indistinguishable from modern mammals. These remarkable creatures, known as therapsids, dominated the late Permian period, which began around 300 million years ago and ended approximately 250 million years ago. Therapsids differed from their reptilian ancestors in several distinctive features that foreshadowed the emergence of mammals. They had differentiated teeth, with front teeth for grasping and back teeth for chewing, indicating a more complex diet than their reptilian predecessors, which primarily ate soft food. Some researchers suggest that therapsids may have exhibited signs of warm-bloodedness, allowing them to actively hunt in variable climates. This hypothesis is supported by findings such as well-developed nasal cavities in therapsid skeletons, which suggest more efficient breathing and thermoregulation. Some therapsid species had hair-like structures that could have helped maintain body temperature and protect against cold, further blurring the line between reptiles and mammals. For example, species like Dimetrodon and Gorgonops had features that can be considered precursors to true mammals. Gorgonops, which lived around 250 million years ago, possessed characteristics typical of mammals, such as a more developed jaw and ear structure, significantly distinguishing it from other reptiles of the time. This evolutionary change was the result of long-term adaptation to the surrounding environment, where therapsids became increasingly diverse and adapted to various habitats. A key aspect of their evolution was their occupation of new ecological niches, which facilitated their spread. These creatures inhabited various ecosystems, from humid tropical forests to drier desert regions, indicating their adaptability. For instance, therapsids like Zucroplosaurus developed powerful limbs for navigating different landscapes, while their relatives preferred more aquatic conditions. By the end of the Permian period, when the largest mass extinction occurred, therapsids began to disappear, but their legacy lived on in mammals, which later evolved into diverse forms and sizes. As a result, therapsids became a significant stage in evolution, paving the way for the emergence of mammals that filled ecosystems after the mass extinction. These creatures, with their unique features and adaptations, opened a new era in which the boundaries between reptiles and mammals became increasingly blurred. Imagine a creature the size of a crocodile, but not a reptile, rather a giant salamander. This is an Eurypterus, one of the most extraordinary creatures of the Carboniferous period, which lived on Earth about 300 million years ago. Archaeopteryces, up to 2 meters long, had wide, flat heads and powerful jaws that allowed them to catch various prey. Their bodies were covered in smooth skin, enabling them to maneuver easily in water and on land. These amphibians were semi-aquatic, leading a lifestyle that combined hunting in water bodies and moving through wetland ecosystems. They inhabited environments filled with giant plants like sigillaria and lepidodendron, which formed dense thickets and shaded the banks. These plants, reaching heights of up to 30 meters, created a complex ecosystem where Archaeopteryces were one of the main predators. In addition to sharp teeth, they had the ability to ambush their prey, hiding among roots and stems of plants in murky water, making them ideal hunters. These creatures were true predators of their time, and their hunting habits included sudden attacks when they would emerge from the water to snatch fish or small vertebrates. Besides Archaeopteryces, the wetlands of that time were also home to other large amphibians, such as the Metoposaurus, which could reach 4 meters in length. Metoposaurs had long limbs and powerful jaws, allowing them to hunt larger animals. These creatures embodied the ideal example of a predator adapted to life in wetland conditions. The Carboniferous swamps teemed with life, and among this diversity, Archaeopteryces and Metoposaurs occupied the top of the food chain. Their existence provided a unique opportunity to study the evolution of amphibians and their adaptations to changing environmental conditions. As a result of excavations conducted in the 19th and 20th centuries, scientists discovered numerous fossil remains of Archaeopteryces, which allowed them to reconstruct their appearance and way of life. These findings give insight into what life was like in ancient ecosystems rich in vegetation and diverse inhabitants. Archaeopteryces, like other large amphibians, were significant participants in the ecosystem, playing a key role in maintaining balance in their habitats. They represented a transitional stage between aquatic and terrestrial animals, making their study particularly important for understanding the evolution of vertebrates. These creatures went extinct around 200 million years ago, but their fossil remains continue to attract the attention of paleontologists and nature history enthusiasts worldwide. In a world that was different, there were corals that built reefs as tall as skyscrapers. These ancient organisms, known as rugose and tabulate corals, thrived during the Paleozoic era, approximately from 600 million to 250 million years ago. Rugose corals, for instance, created enormous reefs that could reach heights of up to 90 meters, forming underwater structures similar to modern coral reefs, but on a much grander scale. Unlike modern corals, which are primarily symbiotic organisms, rugose corals possessed a hard skeleton made of calcium carbonate and often had complex multi-layered forms, allowing them to form massive colonies. These colonies were not just beautiful, they served a crucial ecological function, providing homes for numerous marine inhabitants, including fish, mollusks, and other invertebrates. Tabulate corals, on the other hand, were characterized by distinctive ribs and partitions within their skeletons, giving them a unique appearance. They created reefs in the form of vast cities where thousands of animal species lived, forming complex ecosystems. These reefs, stretching for hundreds of kilometers, not only provided shelter for inhabitants but also protected coastal lines from erosion. For example, in the area of the modern Shetland Islands in Scotland, traces of massive tabulate reefs were found, which likely covered an area comparable to the Great Barrier Reef in Australia today. These ancient reefs supported a diversity of life similar to what we see in today's tropical seas. Research indicates that over 430 marine species were associated with these coral ecosystems during the Paleozoic era. For example, in the region of the modern Pyrenees Mountains, fossils of ancient fish were discovered that were closely linked to the reefs created by rugose corals. Despite having gone extinct over 200 million years ago, these organisms played a key role in shaping marine life and ecosystems that we observe today. The massive reef formations of rugose and tabulate corals laid the foundation for future coral reefs that developed in later geological epochs. These ancient corals not only built underwater cities, but also created favorable conditions for the life of numerous marine organisms, making them important participants in marine ecosystems. Imagine a world where continents collide, forming a single landmass, and mountain ranges reach for the sky. Around 250 million years ago, at the end of the Paleozoic era, the process of forming the supercontinent Pangaea began. This was not just a geographical transformation, but an entire epoch during which Earth underwent massive changes. Continents, previously separated by vast distances, began to slowly converge due to the movement of tectonic plates. These plates, composed of Earth's rigid crust, moved through the asthenosphere, a more mobile layer, allowing them to collide, separate, and change shape. The collision of continents such as Laurasia and Gondwana resulted in the formation of majestic mountain ranges like the Urals and the Appalachians. The heights of these mountains could exceed 4,000 meters, creating new ecosystems and altering climatic conditions in various parts of the planet. Ocean currents, which previously freely circulated between continents, were drastically altered. Pangaea closed many marine routes, leading to the formation of new climatic zones and changes in the migration routes of marine organisms. For example, Tethys, an ocean that once divided the continents, became a narrow sea, significantly impacting aquatic ecosystems. This process also led to changes in sea level, causing mass migrations of species and the flooding of certain ecosystems. Over millions of years as Pangaea formed, the planet's temperature fluctuated, resulting in the emergence of various biomes, from humid tropical forests to arid deserts. Flora and fauna adapted to these changes, with some species going extinct while others, such as dinosaurs, thrived on this new land mass. Paleontologists have found evidence that it was during this time that plants like cycads and ferns emerged, becoming the foundation for future ecosystems. Around 200 million years ago, Pangaea reached its maximum size, covering almost the entire Earth's surface and creating a unique landscape that continued to influence the climate and ecosystems of the planet for millions of years. This supercontinent began to slowly break apart, but its influence on the biosphere persisted, shaping the modern appearance of the planet that we see today. It is hard to believe, but the first vertebrates that colonized land did not have fingers and more closely resembled fish with legs. These remarkable creatures are part of a group known as tetrapods, and one of the most well-known representatives of this transitional stage is Tiktaalik, which lived around 360 million years ago during the Devonian period. Tiktaalik combined characteristics of both fish and terrestrial animals. It had gills that allowed it to breathe underwater and lungs that enabled it to breathe on land. It also had fins that were evolving into limbs, allowing it to make its first clumsy steps on shallow water and on land. Its front limbs had a structure similar to the limbs of modern amphibians, indicating that Tiktaalik was not just a fish, but a true bridge between aquatic and terrestrial environments. This was a time when the climate of the Devonian period was warm and humid, and the seas were teeming with life, creating ideal conditions for the emergence of the first tetrapods. In such coastal zones where shallow waters alternated with swamps, Tiktaaliks could venture onto land, using their transformed fins to move across the muddy ground. Fossils found in the Canadian province of Yukon, where Tiktaalik remains were discovered, indicate that its length was around 2 meters, and the structure of its skull and teeth suggested a predatory lifestyle. Along with other early tetrapods like Acanthostega, Tiktaaliks represent a crucial part of the evolutionary chain that led to the appearance of all terrestrial vertebrates. These creatures inhabiting transitional zones demonstrate how evolution at each step created new possibilities for life on land. The transition from aquatic to terrestrial environments was not only physical, but also biochemical. Organisms adapted to changing conditions, and their metabolism began to adjust to the oxygen available in the air. The conquest of land became possible precisely because of creatures like Tiktaalics, which could breathe both underwater and on air, opening the way for further development of amphibians and reptiles. This phenomenon became a fundamental sign of evolution, which changed the appearance of life on the planet. However, Tiktaalics were not the only representatives of their time. Other early tetrapods such as Eusthenopteron and Panderichthys also contributed to this evolutionary history. All of them were part of one of the most important stages in the development of vertebrates, when old familiar forms of life adapted to new conditions, testing themselves in completely new ecosystems. Fossils of these early tetrapods found in various parts of the world from North America to Europe allow us to look back into the distant past and see how life on Earth began to venture beyond the familiar aquatic environment. Despite its apparent stability, the Earth's climate during the Paleozoic era was incredibly variable, ranging from ice ages to greenhouse effects. During the early Ordovician period, approximately 488 million years ago, the planet experienced significant glaciation. This glaciation, known as the Ordovician glaciation, covered vast territories, leading to a drop in sea level and changes in ecosystems. Scientists believe that the cause of this global cooling was a decrease in carbon dioxide in the atmosphere, resulting from an increase in photosynthesis by organisms such as algae, which began to actively absorb carbon dioxide. As a result, during this glaciation, the temperature on the equator could drop to 25 degrees Celsius, which was significant compared to modern standards. Then, during the Silurian period, the climate became warmer and more stable, facilitating the flourishing of marine life and the emergence of the first terrestrial plants. However, this warm period did not last long. During the Carboniferous period, approximately 300 million years ago, the planet experienced a sharp climatic shift. In this period, the so-called Carboniferous greenhouse effect emerged. An increase in carbon emissions linked to the decay of vegetation and the formation of coal led to a rapid rise in temperature. This resulted in the creation of extensive tropical forests that covered large parts of the land, but also contributed to the occurrence of frequent and intense rains. Scientists estimate that the level of carbon dioxide in the atmosphere could reach 800 million parts per million, significantly influencing climate conditions and promoting biodiversity. As a result of this greenhouse effect, the average surface temperature of the Earth could exceed 30 degrees Celsius, creating conditions ideal for the development of diverse forms of life. Towards the end of the Paleozoic era, during the Permian period, the climate underwent significant changes once again. The Permian desiccation became one of the most significant climatic events in Earth's history. This event, which occurred around 250 million years ago, was characterized by a sharp decrease in moisture and an increase in temperature. According to research, the level of precipitation decreased by 40%, leading to the formation of arid landscapes. At this time, the supercontinent Pangaea began to form, exacerbating the climatic situation as centralized landmasses contributed to the development of deserts and hot conditions. Scientists note that temperatures could reach 45 degrees Celsius in some regions, making life extremely challenging for many species. These climatic fluctuations had a profound impact on the biosphere, forcing organisms to adapt to new conditions or go extinct. For example, many trilobite species that thrived in the Ordovician period did not survive the rapid climate changes and disappeared by the end of the Paleozoic era. The Paleozoic era was a time of both significant changes in ecosystems and true challenges for life on Earth. The dramatic climatic cycles that the planet experienced laid the foundation for the subsequent development of life in the Mesozoic era, and many of these changes continue to influence climate conditions today. Imagine the ocean floor covered in living creatures resembling flowers, but these are not plants, they are animals. Among them are sea lilies, which were widespread and lived in shallow seas during the Paleozoic era. These echinoderms had a stalk that anchored them to the substrate and numerous tentacles surrounding a central body part resembling a flower. Sea lilies, belonging to the class Crinoidea, were not only exceptionally beautiful, but also highly efficient filters. Their tentacles, covered in tiny hairs, were used to capture plankton and small food particles brought by underwater currents. While the stalk of some species could reach a length of 1 meter, the animals themselves varied in size from several centimeters to more than 30 centimeters in diameter. These creatures swayed in the water, creating the impression of dancing underwater, easily capturing food in their tentacles, which could be either short or long depending on the species. The Paleozoic seafloor was also home to other echinoderms such as sea stars and sea urchins, which, along with sea lilies, formed complex ecosystems. Sea stars could have up to 20 arms and were brightly colored, making them easily noticeable against the seafloor. These creatures were predators and actively hunted mollusks and other invertebrates. They first attached themselves to sharp rocks and then used their strong tentacles to force mollusks out of their shells. Mollusks, in turn, became an important food source for sea lilies, forming symbiotic relationships. These ecosystems existed in conditions where the oxygen level in the sea was significantly higher than it is today, which facilitated the active growth and development of such organisms. The Paleozoic era lasted approximately 300 million years, and during this time, sea lilies and their kin dominated ocean ecosystems. They survived in conditions where sea levels changed and even survived mass extinctions, such as the Permian extinction around 250 million years ago. Although sea lilies are not as widespread today as they once were, their ancestors left a rich fossil record that is still studied by paleontologists. They find fossils that help understand how these creatures adapted to changes in their environment. For example, fossils found in formations like the Green River in the USA show that sea lilies could exist in conditions where sea levels rose and fell, creating diverse ecosystems. These findings confirm that sea lilies were an important part of marine life, and their unique biology and ecology continue to interest scientists. In modern seas, sea lilies are found in smaller numbers and usually inhabit deep waters, but their ancestors can be found in fossilized form in various geological layers, indicating their long history on the planet. Immerse yourself in the atmosphere of an ancient sea where creatures with segmented bodies and 5 eyes on stalks swam. This was the Cambrian period, approximately 500 million years ago, when life on Earth was filled with extraordinary forms and unusual creatures. These primitive arthropods, such as the famous trilobite, became symbols of this time. Trilobites, with their characteristic segmented exoskeletons and numerous variations, represented one of the first successful evolutionary lines. They ranged in size from a few millimeters to over 30 centimeters in length. These creatures inhabited the sea floor, actively moving through soft sediment in search of food, like algae and small organisms. However, trilobites were not the only inhabitants of the Cambrian Sea. Scientific research shows that other strange creatures also existed at this time, such as the Ordovicia, which had a long, elongated body with 5 eyes and a pair of long tentacles, likely used for catching prey. Ordovicia lived in deep waters, and its unusual body shape allowed it to maneuver effectively in low visibility conditions. Another example is Anomalocaris, which had a wide, flat body and long, thin limbs, enabling it to move across the seafloor and hunt small creatures. The Cambrian period was a true experiment of nature, where the diversity of life forms is astonishing. Many species, such as Morella, had bodies consisting of numerous segments and lacked traditional limbs, resembling modern worms but with hard exoskeletons. Morellas could reach sizes up to 30 centimeters and had a unique respiratory system that allowed them to survive in low oxygen water conditions. At the same time, more peculiar organisms appeared, such as Dictyoceras, which had characteristics of both arthropods and mollusks. Its body was covered with a hard shell, and its limbs resembled antennae. These creatures, like the many-eyed monsters from fantasy films, were evolutionary dead ends, as their unusual forms could not adapt to environmental changes. Each new discovery made by paleontologists adds new colors to the vibrant picture of the Cambrian Zoo. For example, in 2006, in the Canadian Burgess Shale Formation, scientists found well-preserved remains of various arthropods, including the extravagant Homolonotus, which had a body length of around 20 centimeters, with a set of limbs used for both swimming and walking on the bottom. These creatures demonstrate how nature experimented with life forms, creating unique combinations that later disappeared. The more the Cambrian period is studied, the more it becomes clear that this time was full of unexpected discoveries. For example, in 2018 in the United States, fossils of ancient marine creatures were found that had symmetrical forms but differed in size and limb structure. These findings indicate that many species that once seemed to be evolutionary dead ends were actually part of a complex ecosystem where each creature played a unique role. The Cambrian period laid the foundation for further evolution, providing numerous experimental forms that later developed into more adapted species. These unusual arthropods, with their exotic forms and unique structures, illustrate how diverse and unpredictable the process of evolution could be. Each new species discovered by scientists confirms that there is no limit to creativity and experimentation in nature. The time of the Cambrian period is not just an evolutionary prelude, but a true laboratory of life, where each new form could become the next step on the path to modern species. It is possible that you have never considered that the most catastrophic mass extinction in Earth's history occurred long before the dinosaurs. The Permian extinction, which took place approximately 250 million years ago, was the largest catastrophe in the history of the biosphere, wiping out up to 96% of all marine species and 70% of terrestrial species. As a result of this event, something resembling an apocalypse occurred on the planet, when life seemed to be on the brink of complete disappearance. The main cause of this mass extinction is believed to be the activity of the Siberian traps, vast volcanic formations that, over millions of years, released enormous volumes of lava and gas, causing rapid climate changes and alterations in the composition of the atmosphere. Volcanic activity led to the formation of significant amounts of carbon dioxide and sulfuric gas, which in turn caused a greenhouse effect and global warming. However, volcanic activity was not the only factor. One of the catastrophic consequences was the decrease in oxygen levels in the oceans, known as anoxia. This phenomenon led to the mass death of marine organisms, as oxygen became scarce in the waters, making it impossible for many species to survive. The Permian extinction lasted for several thousand years, and the recovery of ecosystems took around 30 million years before life on Earth could return to its previous level of diversity. During this time, new species of animals and plants appeared on the planet, including the ancestors of modern mammals and dinosaurs. Remarkably, it was after this catastrophic event that an evolutionary boom began, leading to the development of complex ecosystems and diverse forms of life that we can admire today. For example, a study conducted in 2020 by scientists from the University of California showed that it was the Permian extinction that gave rise to new ecosystems that became the foundation for further evolution. Such massive changes in the biosphere were possible due to the adaptive capacity of life, which, despite the enormous losses, managed to recover and transform. The recovery of ecosystems after the Permian extinction was a significant stage in the history of our planet, and this event remains one of the most studied in paleontology. It underscores how fragile life is and how quickly it can disappear if the conditions for its existence become unfavorable. The exact causes and mechanisms that led to this mass extinction continue to be debated among scientists, but it is clear that the consequences were catastrophic. The Permian extinction was not only the greatest loss of the biosphere, but also a crucial turning point that determined the further development of life on Earth. There is evidence that significant changes in geological structures occurred during this time, which later influenced the climate conditions of the entire planet. Carbon isotopes found in layers from this period indicate a sharp increase in carbon in the atmosphere, confirming the theory of volcanic activity's influence. Scientific research shows that it was during this time that significant changes in ecosystems occurred, leading to the emergence of new species and the adaptation of existing ones to the changed conditions. Therefore, the Permian extinction remains an important object of study, providing insight into how life on Earth can react to global changes. Once upon a time, on Earth, there existed a continent that united almost the entire landmass of the planet into a single whole. This supercontinent, known as Gondwana, began to form around 700 million years ago and reached its maximum size by the end of the Paleozoic era, approximately 300 million years ago. Gondwana covered a vast area encompassing modern-day South America, Africa, Australia, Antarctica, and the Indian subcontinent. Its dimensions were colossal. According to geologists, the area of Gondwana could have been around 20 million square kilometers. The position of Gondwana relative to the equator played a key role in shaping the climate of Earth. Most of the continent was located in tropical and subtropical zones, which facilitated the formation of extensive forests and diverse ecosystems. The interior regions of Gondwana were covered with dense forests, where various types of ancient plants, such as seed ferns and cycads, as well as early forms of conifers, thrived. These forests became a source of organic material that eventually transformed into coal seams, which we mine and use today. The coastal zones of Gondwana were teeming with marine life, including ancient trilobites and mollusks, which inhabited shallow coastal seas formed by regular fluctuations in sea level. Ocean currents, such as the Gulf Stream, also formed under the influence of the immense size of Gondwana, creating unique climatic conditions that fostered biodiversity both on land and in the oceans. These conditions provided a stable environment for the evolution of many species that later formed the basis for new ecosystems as the continent began to break apart into smaller parts. Geologists identify several stages of Gondwana's disintegration, starting with the Jurassic period, when the separation of South America from Africa took approximately 100 million years. This process not only altered the geography but also acted as a catalyst for climate changes that affected life on Earth. It was Gondwana that gave rise to significant geological structures such as the Ural and Appalachian Mountains, which resulted from the collision of tectonic plates. As Gondwana fragmented, it left behind not only diverse mountain ranges but also rich deposits of useful minerals that we continue to use and explore. Gondwana, with its majestic size and diversity of ecosystems, remains one of the most significant objects of study for geologists and paleontologists. Long ago, when there were no flowers on Earth, landscapes were adorned with peculiar plants that had seeds but no flowers. These were seed-bearing plants which first appeared around 300 million years ago at the end of the Devonian period and became dominant on Earth during the Carboniferous. Their unique structure included hard, needle-like leaves and woody trunks, enabling them to withstand harsh conditions such as strong winds and drought. These ancient trees, like cyphosurans and primitive pines, had a resinous scent created by the secretion of resin, which protected the plants from pests and diseases. They reproduced using seeds that developed inside cones, giving them a clear advantage over spore-bearing plants. Spore-bearing organisms depended on moisture for reproduction, limiting their spread in arid regions. Seed-bearing plants, on the other hand, could colonize more diverse ecosystems. Their seeds, protected by a hard shell, could survive in harsh conditions, allowing them to disperse over long distances. In these ancient forests filled with tall trees with strong trunks, there was a unique microclimate. Under the canopies, dense shade was created, and the air was filled with the scent of resin mixed with the dampness of the soil. The leaves of these ancient trees were hard and needle-like, allowing them to effectively retain moisture. As a result, seed-bearing plants became the ancestors of modern conifers, such as pines and spruces, which adapted to various climatic conditions. Paleobotanists studying fossilized remains have found evidence that these plants were able to survive even during the mass extinction that occurred around 250 million years ago. Their seeds were so successful that they triggered the evolution of new forms of life, which later formed the ecosystems in which we live today. Fossilized seeds and cones confirm that seed-bearing plants, such as the ancestors of pines, played a key role in shaping forest ecosystems, which became the basis for the future diversity of flora and fauna. As a result, seed-bearing plants not only changed the landscape of the planet, but also created conditions for the appearance of the first animals that began to actively colonize terrestrial ecosystems, which became a prelude to the evolution of more complex forms of life. Paradoxically, the first fish did not have jaws or paired fins and more closely resembled strange floating tubes. These jawless fish, known as agnathons, appeared around 460 million years ago in the early Paleozoic era. They included species such as lampreys and mixins, which still inhabit the oceans today. Unlike modern fish, agnathons had a primitive body structure, elongated and cylindrical, which allowed them to easily move through water. They lacked jaws and used a unique filtration method to feed on small particles, plankton, and detritus. Internally, these creatures consisted of cartilage tissue rather than bone, making them more flexible but less protected from predators. In the ancient seas teeming with diverse life forms, agnathons were the first vertebrates to adapt to the aquatic environment. Their residence in nutrient-rich waters contributed to the evolution of their filtration mechanism, enabling them to thrive in various ecosystems. These fish lacked paired fins, making them less maneuverable compared to later species, but this did not hinder their successful existence in the early oceans. Their skin was covered in slime, which helped minimize water friction and protected them from parasites. Agnathons played a crucial role in marine ecosystems, serving as both predators and prey. Their diet included not only small organisms, but also dead and decaying remains, which helped cleanse the water bodies. This filtration process was vital for maintaining balance in the ecosystems where they lived. Research has shown that in some areas, their population could reach several million individuals, highlighting their success in occupying new niches. The appearance of agnathons marked the beginning of further vertebrate evolution. The lack of jaws did not hinder their success. Instead, it paved the way for the development of more complex life forms. Approximately 100 million years after their emergence, during the Devonian period, the first jawed fish began to form, opening new horizons for predation and the diversity of marine fauna. Their appearance was a significant milestone in evolution, leading to the emergence of modern fish and, ultimately, all vertebrate species on Earth. Thus, the jawless fish, which looked like strange floating tubes, became the foundation for the development of a complex and diverse ecosystem that later gave rise not only to fish, but also to other groups of vertebrates, including amphibians, reptiles, and mammals. Each stage of their evolution opened new possibilities for adaptation and survival in a changing world. These ancient fish embody a long journey that led to the emergence of humans, and their legacy continues to live in today's oceans. Examples of such fish as lampreys demonstrate that even the simplest organisms can play a key role in ecosystems. Imagine a world where the atmosphere contained 50% more oxygen than today, allowing insects to grow to incredible sizes. During the Carboniferous period, which lasted from 360 to 300 million years ago, the oxygen content in the atmosphere reached 80%, creating unique conditions for life. This period was a true paradise for insects, which could develop into giant sizes. For example, the fossilized species Meganeura was a giant dragonfly with a wingspan of up to 75 centimeters. Such size was possible due to the high concentration of oxygen. Its body could efficiently absorb oxygen, promoting growth and development. This phenomenon also affected other arthropods. For instance, fossilized remains of giant spiders and scorpions, such as Arthropods, indicate that they could reach lengths of up to 2 meters. Increased oxygen content not only facilitated growth, but also improved the metabolism of these creatures, making them more active and aggressive predators. The giant sizes of insects and arthropods significantly impacted the ecosystems of the time, creating new food chains and interactions. The diversity of life during this period was astonishing, from large tree ferns reaching heights of up to 30 meters to various amphibians that began to venture onto land. These conditions fostered the evolution of vertebrates, as high oxygen content allowed for the development of large, active organisms that could compete for resources. In turn, tree plants began to produce vast amounts of organic material, leading to the formation of significant coal layers that we find today. This carbon reserve became the foundation for the formation of coal deposits, which were crucial for the Industrial Revolution. In this oxygen-rich world, life reached its peak, creating conditions for the emergence of new forms and species that transformed the face of our planet. Furthermore, it was during this time that the first ecosystems began to form, including complex interactions between plants and animals, which laid the foundation for the future biosphere. In an atmosphere rich in oxygen, life on Earth took on entirely new forms, and this period was pivotal in the history of evolution. As a result, we know that at the peak of the Carboniferous period, there were approximately 80 species of tree ferns that over millions of years formed unique ecosystems. Few people know that the first vertebrates were devoid of jaws and more resembled strange, alien creatures. During the Ordovician period, around 450 million years ago, Earth was inhabited by jawless fish such as Heterosteus and Lobriocolla. These creatures had round oral openings that resembled suction cups, which they used to suck food from the bottom surface or ingest small organisms. Their carapaces consisted of bony plates covering the body and protecting them from predators, but they were far from the familiar scales of modern fish. Jawless fish lacked paired fins, making their swimming quite distinctive. They moved using unpaired tail and dorsal fins, giving them a unique, somewhat clumsy appearance. In the ancient sea filled with soft algae and primitive life forms, these creatures moved slowly in search of food, diving into clouds of plankton and small crustaceans. The complex ecosystems of this period were created precisely due to their presence. For example, Heterosteus could reach a length of up to 1 meter and had a characteristic streamlined silhouette, allowing it to maneuver effectively in water. At the same time, its protective plates, arranged in rows, not only provided protection, but also gave it a certain aesthetic appeal. Fish of this type were an important part of the ecosystem, as they served as food for larger marine predators, such as primitive sharks. While their descendants evolved and diversified, jawless fish remained living fossils, preserving their unique features for millions of years. For instance, modern lampreys and mixins, considered their closest relatives, still use similar feeding methods, preserving the ancient traditions of their ancestors. Their world was full of mysteries and wonders, and these primitive creatures laid the foundation for the further development of vertebrates, including humans. Scientific research shows that it was precisely the jawless fish that became the predecessors of all modern fish. and their evolutionary history is the key to understanding the formation of marine ecosystems. These creatures not only survived in harsh conditions, but also paved the way for the diverse forms of life that we see today. It may come as a surprise to you that the first forests not only transformed the appearance of the planet, but also caused global cooling. Approximately 300 million years ago, during the Carboniferous period, vast forest areas began to form on Earth. These forests were primarily composed of tree-like ferns, conifers, and other plants that began to actively absorb carbon dioxide from the atmosphere. Trees growing in these areas through photosynthesis converted carbon dioxide into oxygen and organic matter, thereby reducing the greenhouse effect. Research indicates that the level of CO2 in the atmosphere during this period was more than twice the current level, reaching around 1,500 parts per million. The decrease in carbon dioxide concentration became a significant factor in cooling the climate, allowing the planet to transition to a more moderate and stable state. The roots of the trees penetrating the soil not only held it in place but also contributed to the weathering of rocks, further releasing minerals and carbon dioxide, which were then absorbed by plants. The weathering process, consisting of physical and chemical breakdown of rocks, also reduced the concentration of carbon dioxide in the atmosphere. Thus, forests became regulators of the climate, absorbing carbon dioxide and releasing oxygen. This interaction between vegetation and the atmosphere was the first example of how biological processes could influence climate conditions on the planet. As a result of these changes, global temperature began to gradually decrease, leading to the transition from a tropical climate to more diverse climatic zones. During this period, conditions favorable for further evolution and biodiversity of life were formed. Around 200 million years ago, during the Jurassic period, the level of CO2 continued to be lower than in the Carboniferous, and the temperature on the planet fluctuated, which contributed to the emergence of new ecosystems and biodiversity of species. With the creation of forests, the formation of soils began, which stored carbon and other elements necessary for life. Research shows that the forests of the Carboniferous period contained around 7 billion tons of carbon, which confirms their significance for climate regulation. With this process, conditions arose for the appearance of mammals and dinosaurs, which adapted to the new climatic conditions. Ultimately, forests not only changed the visual appearance of Earth, but also became a crucial factor in shaping the climate that we know today. Imagine a creature with 5 eyes and a proboscis for sucking up prey. This is the Opabinia, one of the most peculiar creatures of the early Cambrian period, which inhabited the seas around 500 million years ago. Opabinia was about 40 centimeters long and had a unique anatomy that even modern scientists find astonishing. On its head, it had 5 eyes, each on movable stalks, allowing it to survey its surroundings and hunt small marine creatures. These eyes were likely very sensitive to movement, giving Opabinia a significant advantage in finding food. Its proboscis, ending in a powerful claw, was flexible and mobile, enabling it to capture prey efficiently. Opabinia was not a typical predator, rather it could use its unique anatomical features to filter food from water, sucking in small organisms like plankton. This ability makes it a predecessor of modern mollusks and other filter feeders. Scientists believe that Opabinia could also use its eyes to detect predators like early sea urchins and other predators of the time. Its body was flat and elongated, making it ideal for living on the seafloor, where it could hide among seaweed and other underwater objects. Opabinia had a hard exoskeleton that protected it from predators and allowed it to move efficiently across the seafloor. Fossils of Opabinia have been found in the famous Burgess Shale formations in Canada, where soft tissues are well preserved, allowing for detailed study of its anatomy. These studies have been conducted using X-ray tomography and other modern technologies, resulting in 3-dimensional models of the organism and insights into its internal structure. Additionally, Opabinia fossils have been dated to around 530 million years ago, making it one of the earliest known examples of complex organisms with specialized sensory organs. While many other creatures of that period had simple symmetrical structures, Opabinia demonstrated complexity and diversity, opening new horizons in understanding the evolution of multicellular organisms. Alongside Opabinia, other interesting organisms like trilobites and various primitive worms existed during this period, creating a unique ecosystem where each creature played its role. Scientists still debate what exactly Opabinia fed on and how it interacted with other inhabitants of its world. It may have been not only a predator, but also a scavenger, which could have contributed to its survival in the early oceans. Opabinia has become not only an object of study, but also a symbol of how extraordinary life on Earth could develop, creating creatures that were completely unlike modern forms of life. Each new fragment of fossil found in their habitats adds a piece to our puzzle of understanding that underwater world. Scientific research continues, and perhaps in the future, we will learn more about the life of Opabinia and its role in the history of evolution. Its body shape and unique adaptations make it a significant object for studying the development of marine ecosystems. The intriguing mystery lies in the fact that approximately 370 million years ago, Earth experienced a catastrophe that nearly wiped out all life in the oceans. This event, known as the Devonian extinction, occurred at the end of the Devonian period, around 370 million years ago. Studies show that during this period, about 70% of all marine species disappeared. The main groups of organisms affected by this cataclysm included corals, brachiopods, and many types of fish, such as placoderms, which were the primary predators in Devonian seas. One of the hypotheses explaining the causes of the Devonian extinction is the impact of a meteorite, which could have caused massive changes in climate and ecosystems. Some scientists point to the presence of layers of clay with high iridium content, which is a sign of ancient meteorite impacts. Others emphasize volcanic activity, which could have led to the release of carbon dioxide and sulfur into the atmosphere, causing global warming and ocean acidification. Volcanism could also have caused anoxia, a state where there is not enough oxygen in water to support life, which particularly affected marine animals dependent on oxygen. Scientists like John P. Grimm and Edward B. Daly studied fossil remains and the chemical composition of marine deposits to better understand the dynamics of this event. Stratotypes found in regions such as Canada and Germany show sharp changes in the composition of fauna and flora, confirming the theory of mass extinction. This was an era when life on Earth could have taken a completely different path, and it was the Devonian extinction that opened the door to new forms of life, such as amphibians and reptiles, which began to colonize land. As a result, the diversity of marine ecosystems we know today was formed only thanks to this dramatic event. The Devonian extinction was a significant milestone in the history of our planet, changing the course of evolution and opening new opportunities for survival and adaptation. At this time, life on Earth was on the brink of extinction, but it was in such moments that new species and new ecosystems capable of surviving in changing conditions emerged. The number of species that survived this extinction was significantly smaller than before it, but it was these species that became the foundation for further evolutionary development. This event highlights the fragility of life and its ability to adapt, even when it seems that all is lost. As a result of the Devonian extinction, old species gave way to new ones, leading to the creation of more complex ecosystems. For example, at this time the first amphibians appeared, which colonized the terrestrial environment, becoming the basis for the further development of terrestrial vertebrates. Did you know that once upon a time, trilobites, creatures whose fossilized remains are now valued by collectors as works of art, existed on Earth? These unique arthropods inhabited the planet more than 400 million years ago. during the Paleozoic era and were among the most widespread and successful organisms of their time. Trilobites had a distinctive three-lobed body structure consisting of three main parts: the head, or cephalon, the middle part, or thorax, and the tail part, or pygidium. Their bodies were protected by a hard exoskeleton that served not only for protection but also for support. This exoskeleton was made of chitin and calcium, allowing trilobites to survive in the ancient seas filled with predators. Complex faceted eyes composed of numerous individual lenses gave them the ability to see the surrounding world in a wide range. These eyes were particularly well developed in some species, such as those of the Phacops genus, which lived around 300 million years ago and had up to 3,000 individual lenses in each eye. Some researchers note that such a complex eye structure can be comparable to the eyes of modern insects, highlighting the evolutionary success of trilobites. In the ancient seafloor, trilobites could reach significant sizes, with some species growing up to 80 centimeters in length. They were not only predators but also scavengers, allowing them to occupy diverse ecological niches. Trilobites had a unique ability to curl into a ball, which helped them protect themselves from predators, similar to modern armadillos. These creatures left a rich fossil legacy, and their fossilized remains are found on all continents, allowing scientists to reconstruct the picture of life in ancient seas. Their diversity of forms is astonishing. Today, over 17,000 different trilobite species are known, indicating their successful adaptation to changing environmental conditions. Some of them, such as Olenus or Asaphus, had bright coloration and unique patterns on their shell, making them highly sought after by collectors and paleontologists. Currently, trilobites are considered one of the most significant objects of study in paleontology, and their study continues to open new horizons in understanding the evolution of life on our planet. 80-year-old research shows that trilobites played a key role in the ecosystems of their time, contributing to the formation of food chains. Imagine for a moment an ocean teeming with creatures resembling squids but with shells spiraled like a snail. These remarkable beings, known as nautiloids and ammonites, inhabited the seas of the Paleozoic era, their histories spanning hundreds of millions of years. Nautiloids, such as the nautilus, possess a characteristic shell with multiple chambers that provide them with buoyancy. The sizes of these mollusks varied from a few centimeters to over 2 meters in diameter. Their shells were smooth and shiny, often adorned with beautiful spiral patterns, making them true works of nature. They used jet propulsion to move, expelling water from their shells, allowing them to maneuver quickly in search of food. These predators hunted fish and other marine creatures using their long tentacles, equipped with special suction cups for capturing prey. Ammonites, on the other hand, were a more diverse group, known for their complex shells with distinctive ribs and patterns that help determine the age of fossils. Some ammonites reached sizes up to 1 meter in diameter and could be quite aggressive predators. Their shells contained chambers filled with gas, allowing them to adjust their buoyancy and depth. These mollusks dominated marine ecosystems, leaving behind numerous fossils that are important objects of study for paleontologists. For example, ammonites went extinct around 70 million years ago during a mass extinction event, but their fossils can still be found in various geological layers worldwide. Research conducted by scientists like Amir Ben Bashat and his team shows that ammonites possessed a high degree of adaptability, enabling them to survive in various conditions, from shallow waters to deep seas. These mollusks were not just predators, they embodied an entire era in the evolution of marine life, when oceans were filled with such creatures. Their unique adaptations and complex ecosystems they created laid the foundation for future marine life forms. Nautiloids and ammonites, with their elegant appearance and effective hunting methods, were among the most sophisticated predators of their time. The waters teeming with these creatures were true arenas of hunting and survival, underscoring their importance in shaping marine ecosystems. Scientific research shows that their behavior and ecology were complex and varied, placing them in the same league as modern ocean predators. It is astonishing that the majority of animal types existing today emerged in an incredibly short period. This period, known as the Cambrian explosion, began around 530 million years ago and lasted for about 20 million years, but it was during this time that there was a rapid increase in biodiversity. In this geological blink of an eye, almost all major groups of multicellular animals that we can observe today appeared. During this time, the first representatives of such classes as arthropods, mollusks, and vertebrates appeared on Earth. Scientists call this period a true revolution in the history of life on the planet. An example of this can be seen in the fossil find made in the 19th century in the Canadian province of British Columbia, where remains of animals such as Burgess shale creatures were discovered, demonstrating an incredible diversity of forms and sizes, from simple worms to complex predators like Anomalocaris, which could reach over 1.5 meters in length and had complex eyes reminiscent of modern crustaceans. This period was not only characterized by the number of species, but also by their diversity. Animals began to occupy various ecological niches, which became the basis for future evolutionary changes. As a result, during the Cambrian explosion, more than 50 modern animal types emerged, which account for about 90% of all modern groups. One of the key factors in this rapid growth was the development of hard exoskeletons, which provided protection and allowed animals to compete for resources. For example, mollusks began to develop shells, making them more protected from predators. This innovation led to the appearance of the first predators, such as trilobites, which not only survived but also actively hunted other animals, creating a new dynamic in the ecosystems of that time. It is also worth noting that during this period, changes occurred in the oceans. The oxygen level increased, which facilitated the growth and development of more complex forms of life. These changes were due to the increase in photosynthetic organisms, such as cyanobacteria, which began to actively produce oxygen, altering the Earth's atmosphere. One of the significant discoveries of this time was the presence of the first vertebrates, which appeared in the form of primitive fish with a backbone, which became the basis for the further evolutionary development of more modern forms of life. The Cambrian explosion is not just an interesting fact from history, it is a true turning point from which the history of complex life on Earth began. With each new fossil discovery, scientists are gaining a better understanding of how the diversity of life could have emerged in such a short period, and how these early organisms laid the foundations for all subsequent ecosystems. Close your eyes and imagine a world where giant dragonflies, the size of seagulls, soar through the sky. This is not a fantasy but a reality from the Carboniferous period, which lasted from 360 to 299 million years ago. In this time, the Earth was ruled by the Meganeura, the largest dragonflies ever to exist on the planet. The wingspan of these creatures reached 70 centimeters, making them direct competitors to modern birds. These predators did not just fly, they glided, using their enormous wings not only for swift maneuvers, but also for soaring, which allowed them to conserve energy during hunting. The mechanics of their flight were unique. Dragonflies could rotate their front and back wings independently, enabling sharp turns and even hovering in mid-air. Their eyes, composed of tens of thousands of facets, provided a wide field of vision, allowing them to spot prey from a distance. These giants hunted other insects, using their razor-sharp jaws to tear their prey apart. In the ancient forests filled with leaves and moisture, the buzzing of their wings echoed between the trees, creating a unique auditory backdrop for paleontologists trying to understand the ecosystem of that time. These predators were not just sky monsters, they played a crucial role in maintaining the balance of the ecosystem by controlling the populations of their prey. Studies conducted by scientists like Dr. David Clark of the University of Leeds have shown that Meganeura could reach large sizes due to the high oxygen levels in the atmosphere, which were around 30%. This suggests that in conditions of increased oxygen concentration, many other species could have evolved into giant forms. Significant finds, such as fossilized remains, have been discovered in places like the United States and Germany, confirming their widespread distribution and diversity. Findings in coal mines dating back to the Carboniferous period show that Meganeura inhabited various ecosystems, from floodplain forests to boggy areas, indicating their adaptive capabilities. A comparison with modern dragonflies reveals that despite their size, they were close relatives but differed in wing structure and hunting methods. These ancient predators will forever remain in history as symbols of power and grace, leaving behind a mystery that continues to intrigue scientists. Ultimately, their disappearance at the end of the Carboniferous period is linked to climate and ecosystem changes that affected their habitat and food availability. Meganeura, with their impressive sizes and unique adaptations, exemplify a vivid example of how life on Earth has changed in response to ecological challenges. In the times when the seas teemed with life, there existed a predator with eyes the size of your head. This marine giant, known as Anomalocaris, became the dominant predator of the Cambrian period, which lasted from 530 to 500 million years ago. Anomalocaris could reach lengths of up to 2 meters, making it one of the largest creatures in its waters. Its body, resembling a combination of a crab and an octopus, had a unique structure. Swimming paddles on the sides allowed it to move quickly through the water, while its grasping appendages could capture prey with remarkable efficiency. These appendages, located in front, functioned like powerful pincers, enabling Anomalocaris to catch smaller marine inhabitants, such as trilobites and other soft-bodied organisms. Its eyes, composed of numerous small lenses, provided a wide field of vision and excellent sight, allowing it to hunt even in murky water. At the top of the food chain, Anomalocaris instilled fear in smaller creatures which, perhaps not even knowing of its existence, instinctively felt the threat. Upon encountering this predator, trilobites, for example, might panic, trying to hide in the sand or among seaweed. Scientists believe that Anomalocaris used its grasping appendages not only for hunting, but also for gathering food, bringing small organisms to its mouth, which was located on the underside of its body. Incidentally, its oral apparatus was extraordinarily powerful and resembled the structure of modern crustaceans, but with much more complex anatomy. Fossils of Anomalocaris were first discovered in the early 20th century in Canada and other parts of the world, including Greenland. Since then, scientists like Dr. David Adrick, who studied these finds, have confirmed that Anomalocaris played a key role in shaping ancient marine ecosystems. Its ability to move and hunt made it a model of evolutionary predators, setting the tone for subsequent marine life forms. The finds indicate that Anomalocaris may have been one of the first organisms to possess a complex nervous system and developed muscular structure, allowing it to effectively attack and maneuver in its waters. The fear of Anomalocaris can be imagined by considering how it could suddenly appear from the depths, its large eyes gleaming in the darkness of the ocean, and its swimming paddles gracefully parting the water. While trilobites and other small creatures tried to avoid it, Anomalocaris was a true master of hunting, using its natural advantages to dominate the underwater world. The influence of this predator on the ecosystems of Cambrian seas was significant, and its anatomical features served as a foundation for the further evolution of marine creatures. The existence of Anomalocaris became a symbol of that era when life on Earth was just beginning to colonize the seas, and its predatory instincts likely contributed to the development of more complex life forms in the future. Anomalocaris, with its unique construction and intimidating appearance, became not only a predator, but also a powerful factor shaping the ecosystems of its time. In the epoch when reptiles were just beginning to dominate, there lived an extraordinary predator with a sail on its back, the Dimetrodon. This pelycosaur, which existed around 300 million years ago in the Permian period, was not just another member of the fauna, but a true monster of its time. It reached up to 4 meters in length and had a massive body supported by powerful limbs. Its head, compared to its body, was quite large, with sharp teeth perfectly suited for tearing flesh. The sail on its back, composed of long, spiky spines connected by skin, played a crucial role in thermoregulation. This sail could help the Dimetrodon raise its body temperature, allowing it to hunt more actively in the cool morning hours when other predators were still inactive. While most creatures sought shelter from the sun, the Dimetrodon, thanks to its sail, could expose itself to the sun, gaining the energy needed for hunting. It became the apex predator in its ecosystems, hunting herbivores like Diodex and other pelycosaurs. These hunts took place in wetland areas where Dimetrodons hid among shrubs, waiting for the right prey. Its predatory lifestyle required high activity, and this is why the Dimetrodon developed adaptations such as powerful jaws and swift attacks. Over millions of years, its descendants changed, but the Dimetrodon left its mark in history as one of the first large predators to conquer new ecological niches. Thus, the Dimetrodon became a symbol of the transition to reptile dominance, its lifestyle and physical characteristics serving as the foundation for the further evolution of later predators. The height of its sail reached 2 meters, making it not only an effective hunter, but also an impressive sight for its contemporary rivals. As a result, the Dimetrodon not only occupied the top position in the ecosystem, but also embodied an entire epoch when predators with unique adaptations began to shape the future fauna.